So as Laurence just said, Christophe was supposed to give this 4-hour lecture on high-performance programming, but he got injured this weekend and couldn't make it. So I'll try to take up on his slides on the topic, well, the best possible. Here is more or less the outline of what I would like to talk about today. I'll start with a brief introduction on why we need high-performance programming and what can be achieved with it. Then I'll take some time to talk about random number generation on parallel architectures, which requires some care if you want to really make sure everything goes well. And then I'll finish with talking about OpenMP, which is a way of programming multi-core architectures. Okay, so let's start with some introduction and motivation on the topic. Everything starts with noticing that sequential programming has become somehow limited. Most of actual applications are actually parallel. For instance, if you take your browser, most of modern browsers simply spawn one process per web page. So this is an example of a parallel application that everyone uses today. Well, I say that sequential programming is limited, but not only because the computing resources are limited, but also, and mainly often, because access to the memory is limited. We'll see that later on, but memory has become a real bottleneck in many applications. You can actually carry on the computations much faster than you can access data. The third point, and probably one of the most important one because it has driven the evolution of modern architectures, it has become much easier to increase the number of processing units than keeping increasing the frequency of a single processor. For a long time, the frequency of processors was doubling every 18 months or so. But doubling, well, actually that was not really the frequency that was doubling, but rather the density of transistors on a chip. But actually doubling, well, increasing the number of transistors you put on a chip like this raises several questions, and one of them is how do you cool all this? Because one of the major problems when you keep increasing the frequency of your processing units is that such a high frequency creates heat, and then you need an efficient cooling system. So sequential programming is limited, but I mean, hardware is also evolving quite a lot, and we have now very common architectures with many cores, and sequential programming is not able to make the most of them. So when I say hardware is becoming faster, yes, if you count, for instance, the number of floating point operations that you can achieve with your hardware, but your hardware is actually split in several processing units, and each of them can only handle fewer operations. So if you want to really achieve the peak performance of your hardware, then you really need to use parallel programming. Well, so first I would like to talk a bit about a very famous ranking in the supercomputer world, sorry, which is the top 500. So you can just go to top500.org and you will find such a graph, for instance. So, first of all, what is the top 500? This is the ranking of the largest 500 supercomputers in the world. So this ranking is, well, this is based on a linear algebra problem. So I don't say that that the first supercomputer is in the ranking is really the best one for your problem, but well, this is one way of measuring supercomputers between them. And more than the ranking itself, what is important is the information we have on these supercomputers. So in particular, we have their architectures, the number of cores, the number of processors, the number of floating point operations they can achieve per second. We have the nominal information and also what they actually achieve during the test. So if you look at this graph, so the red curve is the last supercomputer in the ranking. The blue curve is the first one, and the yellow curve is the sum of the floating point operations that could be achieved per second by the sum of all of them. And this is the evolution over time. And here you have the number of floating point operations. And so this line, this one, is the number of floating point operations achieved by a fairly recent laptop, the MacBook Pro of last year. Okay, so what is interesting is to notice is that if, so this point here is in 2002 or 3, I don't remember exactly, but if you take your MacBook and put it in the competition back in 2002, you would have been lost. Okay? But if you go back a little earlier, let's say in 1997 or 1998, then you would have been in the top best. So you see the evolution is quite impressive. Okay. Oh, yes. I thought there was a nice picture there, but it's probably somewhere later. So I have a picture of a supercomputer just to give an idea of what it looks like. And you'll see that it has nothing to do with a laptop. This is usually a huge room full of racks and so on. So here are the goals of high-performance computing. Well, of course, this is dedicated to intensive computation. Well, there are actually several goals depending on what you really want to do. Of course, it can be used to solve a problem faster. Okay, this is probably the first goal people think of. But it can also be used to handle more complicated models, refined models, or you can expect to within the same wall time, you can expect to improve the accuracy of the model you compute. And you can also just want to use high-performance computing to improve interactivity, get the answer faster. Okay. So this is what we put here in more details. Improving the rate means that you want to solve several problems simultaneously, which is quite different from trying to solve a given problem faster. Sometimes it's not that possible to achieve this goal easily. So I mean, solving several problems simultaneously is quite easy, actually. If, as it is written here, that your problems are independent, then solving them in parallel is something simple. Whereas solving a problem faster can become quite difficult depending on the problem you are tackling. And we'll talk about this later on in the section dedicated to measures of performance. And well, the last point is somehow related to the first one, because trying to solve a more refined problem in the same time as the classical problem you are solving is also something not so easy. And well, it's not because you will have twice the number of processing units, then you'll be able to solve them in half the time. And most of the time, well, you won't achieve this this speed up. There's a waste, and this is what we call the efficiency of the parallelization, and we'll talk about this later on again. Okay, so there are actually several ways to achieve parallelism, to put some parallelism in your code. Well, as I said earlier, architectures have become parallel. Everyone here has a laptop with several cores. And related to these architectures of processing units, you also have the architecture of the memory that plays a crucial role in this. The way the different cores or processes are connected to memory is something really important when you want to design a parallel application. Well, and I also mentioned in here accelerators, like for instance GPU or Zen 5 or, well, others. But I won't talk a bit about this. These are actually, they can't work on their own. They have to be associated to some CPUs. And their programmation is something rather specific. Of course, they can be, they can achieve really impressive performances on some specific problems. For instance, well, I have in mind the case of GPUs. If your goal is to implement parallel Monte Carlo, then it will probably be very, very efficient. But as soon as the problem becomes more complicated and more communications are involved, the story starts to change a bit. Well, some compilers are able to introduce a low-level parallelism automatically in the application, but all these automatic use of parallelism are obviously not as efficient as what you could achieve if you had done it yourself. But I mean, this is already a starting point. Of course, one simple way to introduce parallelism in your code is, well, for instance, imagine you have a code using linear algebra. You just have to rely on a parallel linear algebra library, and that's done for this part of the code. Done. Hopefully done, depending on how everything was built inside. The two last points are rather important. I mean, when you start with a mathematical problem, okay, and you have your favorite method to solve it, and then you turn to the implementation, and you say, well, I want to make a parallel implementation. And you start to look at your, let's say, sequential algorithm, or the algorithm you write mathematically, and you start wondering how I can make it parallel. Well, most of the time, this is definitely not the way to proceed, because when you chose the method you are going to use to solve your problem, you had already made important choices, and perhaps choices that were incompatible with paralleling, or at least choices that were not going to help you achieve a good parallel algorithm. I'll come back to this point later and during the training session. When you know in advance that you want to design to implement a parallel algorithm for solving a given problem, then you have to choose among all the available methods the one that suits parallel programming the best. And sometimes, quite often actually, this is not the method that will produce the best results in a sequential program. Okay. So let's talk about a bit about the hardware evolution. This describes what modern hardware looks like. So you already have some implicit parallelism inside. You have several instructions can be run in parallel in the different processes you have, or in the different cores you have, and all this happens automatically. The architectures we have now is this one. So you have multi-core and multi-core and multi-processes most often. So we call this multi-CPU. This is what is commonly found in your laptop. And the good feature of these architectures is that all the computational units share the same memory. And this is a very important point, and this is the starting point of the last part I want to talk about today, which is OpenMP. Okay. And the second architecture we will talk about in this short lecture is what we call clusters, which actually describes any aggregation of computing units. Well, very often this is just so you have cores. Many cores are grouped in a processor. Several processors are grouped together to give a node. Okay, this is what you have, for instance, when you take one computer. Okay, you have several processors. This is what we call a node, and you gather several of them together, and you come up with a cluster. So in a cluster you have, well, you can see a cluster as many processes linked together through a fast network interconnection. Okay, so of course several of these processes are actually sharing the same memory, but well, you can make as if they are all connected through the network. So in such systems, each node has its own memory. This is the main difference with the previous type of architectures, the multi-core architecture, in which you have the same memory for everyone. Here, each node has its own memory, and this so programming these architectures will be the topic of tomorrow's lecture on MPI. Okay. Well, I don't want to talk about accelerators today. So, here is the picture I was looking for. So this picture is this is the Curie supercomputer, which is actually 85 in the top 500 ranking. Okay, so see, this is well, a supercomputer is something quite impressive. So in this you have, of course, all the processing units. There are tens of thousands inside, but you also have the cooling system. And this is what makes supercomputers so huge and expensive. Something good to remember is that when you build a supercomputer or buy a supercomputer, which usually costs something around several millions of euros, in the 3 coming years you will more or less pay the same amount only for the electricity to make it run. And most of the electricity is unfortunately used for cooling, which is a complete waste. Okay. Okay. So the question is, how can you increase the performance of your code using high performance computing? Well, the basic idea is to try to divide a huge task in several subtasks and execute, well, solve them in parallel on different processing units. This raises several questions. The first is to try to identify at which level you should introduce parallelism in order to achieve the best performances. Well, this is not always so easy. It may depend on the number of well, on the size of the architecture you actually target. So very often you have to design your own solution to match the constraints of your problem. Okay. So here are a quick recap of the limitations you have in sequential programming. So you have the limitation of the clock of your CPU, raising several problems as the power consumption and also the problem of cooling, which is non-compatible with mobile devices. Actually, you don't want your smartphone to drain its battery before the end of the day, hopefully. or to produce too much heat. Okay, and this has become quite an issue. Well, there are standard ways of improving a bit your sequential code. But if most of them, if not all of them, are actually automatically endowed by the compiler, and you can't do really much about this. So even if you think that you're actually writing a 100% sequential program, well, at the end, at execution time, there will be some parallel instructions inside, thanks to different mechanisms already implemented in the processes, for instance, such as such as these instructions. And then you have some more elaborate mechanisms that can come in, such as the branch prediction or this. Okay. But I mean, of course, you can gain a bit with all these optimizations, but this will be quite limited. You cannot expect to divide by 2, for instance, the computational time. There's no hope. If you really want to cut down on the computational time, then you really need to do specific things. Okay, so here is the so-called Flint classification, which creates groups of models of programming depending on the architecture you have and the type of data you're manipulating. So what's really important is the nature of the data flow you have and the way you want to apply the instructions. So you have actually 4 cases. You have the case of multiple data with a single instruction. This is typically what GPU does. Just imagine that you have a matrix and you want to apply the same operation on each entry of the matrix. So this is SIMD, and this is what GPU does. You have the case of, well, this single data, single instruction corresponds to the sequential architecture, no paralleling inside. You have, oh, this is a misprint. This M is an S. So you have single data and multiple instructions. Well, you have to be very careful if you want to put parallelism inside. Doing several things at the same time on the same data is not so easy. And the last one, this guy, multiple instruction and multiple data. Well, this is actually the very general type of parallelism you can think of. And this is typically what the multi-core or clusters architecture can do. Okay, and well, and in this lecture, this is this model that we target. Okay. So I said at the beginning that using parallelism, we were not only trying to achieve more operations at the same time, but we were also aiming at having more memory at hand. So this is not really that we want more memory, well, even though sometimes it might be the case, but we also want to be able to access more data within the same time. So here is a typical example of the memory hierarchy you have on a computer. And the one that's important for parallel computing is the cache memory. This is the memory that's closest to the core. And of course, because this is the one that's closest to the core, this is the one you can access fastest. Okay, so if you want to, if you want your parallel application to be efficient, then you probably want to use some locality of the memory and try to access from a given core the memory that's not far from it. Okay, if you have to work on a large amount of data and from the core there you access the memory there, then you're doing everything wrong. So local memory is much faster to access. This is something important. So let's take an example. Imagine you want to compute the sum of two arrays, and these arrays are not in the cache, in the caches of your cores. Okay, so before to access the data, you have to move these three arrays actually to the cache memory. Then this operation, achieving this, fetching the data, accessing the data costs around 10 times much than actually computing the sum. So this is this is something really impressive, and it's good to know when you want to implement a parallel algorithm. You really have to take care of the memory. Okay. So in the next few slides, I want to go a little bit, study a little bit into details what kind of memory we have. So first I will talk about shared memory, which corresponds to what you have on multi-cores architectures. Just to make it precise, when I say multi-core, I have in mind a single computer with multi-processors, each of them having multi-cores. Okay, this is what I call multi-core. Because, if I say multi-processors, people will think that I have in mind clusters, which is something different. So multi-cores is typically your laptop or something larger. I mean, you can have shared memory architectures with 100 cores divided in several processors. Well, this is was about to say common. Common is probably a little bit too strong, but this is not that rare. Okay, so shared memory is what you find in multi-core architectures. In such architectures, all the processing units access the same memory. Of course, you have a hierarchy, but in the end, if you go to the bottom level, each of the processing units can access it. And so there's no way to implement communication by yourself, because you just can access the variables used by your neighbor, so no problem. So actually all the communication is achieved by using shared variables. Okay, this is the good thing of this model of parallel programming. So each processing unit can carry out its own task independently of the others, can manipulate the variables and so on, no problem. But as soon as one of them makes a modification on a shared variable, then it's immediately, or let's say almost immediately, visible by all the others. Okay? So any change you make on the shared variable is becomes visible to anyone. In shared memory architectures, you have two kinds of topologies of memories. Either you have something which is called SMP for a symmetric multiprocessor. Well, this typically corresponds to this scheme. So you have many cores, and they are all plugged to the same memory backbone, and so they can all achieve the global memory at the same speed. Okay? No difference between all of them from the memory point of view. On the contrary, you have this NUMA architecture, which stands for non-uniform memory access, in which all the processors can obviously still access all the memory, but definitely not at the same cost. So a typical example is this one. So you have several memories which are actually linked together. So it could be represented as one block of memory. But the processing units that are close to a part of the memory can access it faster. So of course, when you have such when you target such architectures in your application, you have to make sure that when you place your data and create your thread, all this is done accordingly, such that with one thread here, you access the memory that's here and not the one there, because otherwise you lose a lot of time. Okay. Well, and when you have such a memory architecture, you do it well, you decrease the risk of bottleneck when accessing the memory. Well, so that was for shared memory architectures. At the opposite, you have the distributed memory architecture, which corresponds to what you find in clusters, in which each node, or I write here processor, it's not correct to write processor, because you may have several processes grouped together and that have some shared memory, but let's keep processor for now. So each processor has its own memory, and anything it does on it can't be seen by the others. So any communication between two processors has to be done by hand. You have to initiate communication by yourself, and this communication goes through the network. So, of course, this is more difficult to program, because you have to take care of the communications yourself. Each time you start a communication, there's some overhead in your code, you have latency problems. It really requires some care to do it well. But the good news is that such architectures scales easily. I mean, you won't be able to find shared memory architectures with thousands of cores, whereas you can find several thousands of cores, well actually millions of cores in some supercomputers using distributed memory. So of course inside this distributed memory you have some groups of shared memory, but on the larger scale it's just several independent memories that are connected together. Okay. So programming distributed memory is the topic of tomorrow's lecture. Okay. Okay. So, just to sum up a bit how it works at execution time, you start a process. Actually, you can have many of them running simultaneously, and then in each process you can have multi-threads. Okay. So typically what you will, each thread will do something smaller, and processes are usually started at the very beginning and they live till the end of your program, whereas threads can be created and deleted several times in the life of your process. Well, so this now we talk a bit about the different model of parallelism, and they are actually mapped to the architectures you have. So either you have a distributed memory architecture, and then you need something to communicate. So typically we'll talk about MPI tomorrow. So no shared memory, you have to take care of exchanging data by yourself, or you have a shared memory architecture, and then you have a global memory. It won't scale so much, but for, let's say, a few dozens of cores, it will be fine. And you have, you may encounter something which is, what we call here implicit, which is typically what happens when you use scripting languages such as R or Python, and you use some dedicated packages which implement themselves a parallel program for something, for solving something very specific, and all this is hidden from the programmer, so you already have access to some parallel computing without actually doing it by yourself. Of course, you cannot expect these implicit usage of parallel programming to be as efficient as what you could do in these cases. There's no magic in all this. I mean, if you're not ready to really pay the price, you cannot expect to achieve the maximum efficiency. So just to finish this first part on the introduction to high-performance computing, just want to talk a bit about measuring performances. So probably the most important metric is scalability. The question is, okay, you have your parallel application which is running on, let's say, 10 cores. What happens if now you have 20 cores? Are you going to divide your computational time by 2 or not? Well, in an ideal world, you would divide it by 2, but this is, well, usually if you manage to divide it by 1.9, for instance, you will probably be already quite happy. So this is what scalability is about. This is a metric that indicates how efficient a parallel program is, how efficiently it uses the resources at its disposal. Okay, so it's typically measured by what we call the speed up, which is the ratio of the time required by, well, the time needed to run on one processing units divided by the time needed to run on n processing units. Okay, so of course, at best, this guy is the numerator divided by n. Okay, so S of n is always smaller than n. Okay. The closer it is to n, the more efficient is your application. And well, this measure is sometimes rescaled, and we call it the efficiency. So it's just the speed up divided by n. This gives you a number between 0 and 1. So 1 means that you have a perfectly parallel application. When you double the resources, you divide by 2 the computational time. And usually, well, when the efficiency falls below 1/2, we tend to consider that you have some kind of inefficiency in the application. Well, obviously, the evolution of these measures depends very much on n. Imagine you start with a sequential application that takes a day, okay, and then you have your parallel implementation, and you run it on several, let's say, processors. You run it on, let's say, 24 processors, and it runs on a little more than an hour. So you say, well, okay, fine. I have an efficiency of almost 1. But then, as you will continue increasing the number of resources used, the efficiency will start to decrease a bit. And if in the end you come up for a given n that you will compute by yourself at a computational time of 10 seconds, and you say, and your efficiency is 0.6, for instance, well, you won't deduce that your application, your parallel application, is inefficient. It's just that you've managed to reduce the computational time so much that there's no use trying to involve more resources to run your application. It's just you've somehow reached the ultimate goal you could achieve. And a last word about scalability and efficiency. All this is very much related to the ratio you have in a given code between the parallel part and the sequential part. Usually, even in a parallel application, you have a sequential part inside, and this actually gives you, well, the time required by the sequential part actually gives you a lower bound on the total computational time of your application, no matter the number of processing units involved in your computation. Okay, so this is what Amdahl's law is about. Okay. Before moving to random number generation, I suggest we take a short break. Perhaps if you have questions before, I will be happy to answer.
Thank you. What is the difference between a core and a CPU?
For now, we'll say that there's no real difference. Okay, just use one or the other.
I can show you a picture about the hardware,
Yes.
which show you which resource shared code inside a CPU. I show you after the core shared some resources in the CPU, and there is one socket for access to device per CPU, and core shared this socket to access these resources. Yes.
So, for example, every core has one register, but then the rest of the memory is shared.
Yes, yes, but one access for every core to this memory. Yes. If you have two CPU in one node, we have two sockets, and each core access with the same memory with the socket of each CPU. Yes. I show a picture.
How we can get the optimal number of the CPU when we design an architecture? It depends on the program, or is there any general way to do it?
Well, there's no rule to know in advance how the optimal number of what you call the optimal number of CPU to be used. Well, it depends on the application. It also depends on the sequential running time. Cool. So let's start after this short break. So in the first part, I talked about generalities on high performance programming. Now I would like to move on a more specific topic related to random number generators on parallel architectures. So here are the constraints. Well, you expect that everything goes well on each processing unit, which means that the random numbers you will use in each core, let's say, are independent of each other, and that they have, well, the good statistical properties that you expect from a random number generator. Of course, this should hold true in each core, but it should also be valid when you take all the cores together. So this means that the sequences of random numbers you have on the different processing units must be independent also, and that when you take the sequence obtained by all the random numbers you've used on all the processing units, this looks like a sequence you would get on a sequential architecture from a random number generator. Okay. So these are the constraints, and of course, well, you would like that using random number generators does not incur any overhead in your code, well, as far as possible. Okay, so just to start, I'd like to say a few words on what a random number generator is. Random number generators are actually deterministic sequences with good statistical properties, which means that when you look at the numbers obtained, well, it looks like they come from a sequence of random variables. So what we have in mind when we say it looks like, we think of independence, uniformity, they all have the same law, and of course because the sequence is deterministic and all this is actually coded as integers, your sequence is periodic and you expect that the period is the largest possible. You want your generator to have a small memory footprint and to be fast. Of course, drawing random numbers is some kind of an atomic operation when you try to solve a probabilistic problem. So this is something that you definitely want to be fast. A random number generator can be seen as a state machine with a finite number of states. Formally, you need these three elements to define a random number generator. Some initial state called the seed in the literature. You need a transition function to move from one state to the next, okay? And you need a value function which takes a state as parameter and gives you what you call the random number. Okay. So here is the implementation of probably the most famous random generator, Mersenne Twister, which is actually quite complicated. So all these sequences are recursions, and the depth of the recursion depends on the generator. So in this, so for the Mersenne Twister, n here is the degree of the recursion. M is an integer between 1 and n, and then the way you compute the next state with the previous ones. So you see to compute when you're at a given state to compute the next one, you need many of the previous states, okay, and they are combined together through this operation and multiplication by matrix A, on which I'll come back just in the next slide. Well, and this is just some shuffling of the less significant and most significant bytes. Okay, so this is not important, just to give you an idea of how complex it can be to get a good random number generator. So the important thing here is that for Mersenne Twister, A is called the recursion matrix. And this will play an important role in a few slides. Well, in this one actually. So this matrix A looks like this. It's, well, when it's empty, it's just zeros, and you have a super diagonal of 1, and you have this vector of A's. And this one is important. This one will be used to design a parallel Mersenne Twister. So we'll come back to this later on. The good thing about the design of Mersenne Twister is that the computation, well, this matrix operation, x times A, is actually only computed by shifts. So it's very, very easy. Actually, Mersenne Twister is actually 4 times faster than the basic round generator from the C library. Okay, so it's very, very fast. And for the reference implementation of Mersenne Twister, which is this one, I mean, the period is just Google. It's so huge. You can't even imagine of having a deterministic sequence with such a huge period. I mean, even when you write it as a power of 10, then you have still have more than several thousand as an exponent. Is just unbelievable. And well, and the memory you need to store the state of your generator is actually quite small. Well, I write it 624 words as 32 bits. Well, this means 312 double numbers. So, I mean, it's quite a small array for today's memory. So, what do we expect from a parallel generator? Well, we would like it to be reproducible, and this has to be made precise. What we would like to do is to be able to replay a run using the same number of processes. Because you'll see afterwards that when you change the number of processes, reproducibility becomes an issue. You would like that the sequences that inside the process the numbers are independent, that between 2 processes the numbers are also independent, and of course you want to avoid as much as possible as much communication as possible. Hopefully you don't need any communication, and we'll see that that is indeed possible. So there are actually 2 strategies to design parallel random number generators. The first one is called splitting, and the second one is parameterization. So splitting, well, the idea of splitting is basically to take a sequential generator and to split it in several pieces and try to link a piece of the original sequence to a given processing unit. I will detail it in the next slides. And well, parameterization is, well, the question behind this is, if you still have my Mersenne Twister example in mind with this matrix A, the question is, how do you choose A? What happens if you have 2 generators with 2 different A's? And the answer behind this method is that, well, if you have 2 generators with 2 different matrices A, then they are independent. And then you have to, well, you can't, obviously you can't choose A, you have to choose A with care, otherwise the properties of your generators are not good, but at least if they are different, then the associated generators are independent. Okay, so let's talk a bit about splitting. There are actually 2 ways of implementing splitting. The first one is this one. So you make, well, you actually extract a subsequence from the original sequence. So, for instance, the first processing unit will take the black subsequence, the second one the red, the third one the yellow, and so on. To implement this, you have to be able to make a jump over a certain number of elements at each iteration, and you expect it to be as fast as just sampling one number. Okay. Well, the real drawback of this method is that as soon as you change the number of processors, then you change the way you split the numbers, and so there isn't much hope to ensure reproducibility in this using this way of splitting. Well, there's a huge literature on the parallel random number generators, and in many papers they noticed that extracting a subsequence such as these ones, which rely on a very regular pattern in the original sequence, is actually very bad from the point of view of correlation. Well, this is something you wouldn't probably expect from a random number generator, whereas it is crystal clear for quasi-Monte Carlo. If you take a quasi-Monte Carlo sequence and you extract a subsequence, then you know that you're doing everything wrong. It will probably be nonsense in the end. Well, it turns out that for random number generators, it's almost the same. Okay, so another way of splitting a generator is to split it in block. So you do it this way. You say, okay, I have that many numbers at my disposal, and I know that I will use P processes. Okay, so I just split it in P blocks, and this will be for the first unit, this for the second one, and so on. The mechanism is a bit different from the previous method. In this method, you just need to be able to make a jump at the initialization, because for instance, for the unit 3, you need to be able to jump there, and then for the following calls, it's just a matter of going from one state to the other, so it's easy. Well, as in the previous method, splitting reduces the period of the generator. I mean, this is just somehow inherent of the method. Well, very often we can only handle jumps written as a power of 2. Okay. So this means that probably you will actually won't split your initial generator in blocks of in P blocks, but in a power of 2 larger than P, if you do so in this way, you know, you will come up in the end with a computation involving some random numbers coming from there, but also from there. And these parts are actually very far away in the original sequence. This is something bad. You definitely don't want to put together two parts that are so far away in the original sequences for the same reason as before, because then you're actually turning very long range correlation into short range correlation, and this is something bad. So using this mechanism, what people do usually is say, okay, overall my program won't need more than 1 billion random numbers. Okay, so n is 1 billion, and then you'll say I won't target more than 1,000 cores. So you take P to be so for P you take the smallest power of 2 greater than 1,000, and you're done. This will work fairly well. Okay. well, nevertheless, you need to be able to compute this jump. And you definitely don't want to draw all the numbers up to 2 to the I. Okay? So either there's a simple way to compute the power of your recursion matrix, I mean, just to be able in one step to jump over several steps. Either you need dedicated libraries, and this is the case with Merson Twister. I'll come back just after. Well, okay, so as far as Merson Twister is concerned, well, as the period is so large, when you split it, then you still get an enormous period. I mean, you just can't imagine how huge it is. This generator has a very interesting property, is that its long-range correlation are almost zero. So you won't be able to see it in practice. So, so actually, you can. This generator is very robust. You can take it, split it, using the way you want, and it will work fine. And hopefully there's a library which implements the splitting for Merson Twister, because you remember the recursion is quite tricky. So computing the ith power of the matrix A is definitely not something to be able to do, especially because at each iteration there's this shift in, well, swap in bits between two different states. So it's quite complicated, but there's an open source library doing this. So this is the good news about the Merson Twister. The bad news is that this library weighs something like 20 or 30,000 lines of code just for the generator. Just because splitting Merson Twister is so complicated, but it's really, really fast. Okay. I'll come back in a few slides on the available solutions today. And so the second method is parameterization. So one thing I want to make very crystal clear is that changing the seed of a generator does definitely not ensure the independence of the associated random number generators. Although this is so commonly used in industry today. So what you have to do is, when you try to parameterize a random number generator, is create streams associated with different matrices, well, different recursion matrices. So as far as Merson Twister is concerned for this approach, what is done is that, you know, this matrix A is actually parameterized only by the vector A that was in the last row. So you split this vector in two parts, and you reserve the first bits to store a unique identifier, which will be related to the index of your thread or the rank of your process. And then you're left with some non-filled elements in the vector. And this remaining part of the vector A is chosen or is filled at random. This is something a little strange because you know, if you just want to design a Merson Twister generator and take any matrix A, it probably won't have good properties. The period will probably be maximal. the independence, well, of course the numbers will be independent, but nothing guarantees that they look like identically distributed. So to have all these good properties, you have to choose the matrix A with care. The problem is that if I give you a matrix, you're able to decide whether it's a good matrix or not, but you will never be able to construct one. And this is the reason why the remaining part of the matrix is just filled at random, is because that's the only strategy for actually computing a good recursion matrix. You just use the first bit to encode your identifier, and then for the rest, you just try, you fill it and try to see if it's a good recursion matrix. If not, you just throw it away and you fill again and try and so on. So it's actually a probabilistic approach to create independent random number generators using parameterization. Which means that if you're unlucky, it may take some time. For instance, for the case of Merson Twister, the implementation is called Dynamic Creator Merson Twister. The time required by the initialization depends very much on the number of generators you would like to create at most. So if you say I will never need more than these many random number generators, then you only need 16 bits for encoding the index in your matrix A, and finding a good matrix A is very fast. It requires, it's almost instantaneous. Okay. But if you say, well, this is not enough for me, I want to go beyond that, then the picture does not look so nice anymore. It starts to take a little more time, because of course if you increase this, then it doesn't mean that you're reducing the parts to fill. It means that you have to enlarge the size of your matrix A. So if you do this, it means that you need to enlarge the footprint, the memory footprint of your state, so that actually you're dealing with a much larger Merson Twister random generator. Okay. As far as the training sessions are concerned, we installed a scientific library on the parallel computer you will use, which is called PNL, and the dynamic creator Merson Twister is available through this library using these three functions. So you create a generator using this one, you free it, and then you initialize it. Well, the other way around, actually. Okay, so this is just for practical information for tomorrow. So the takeaway message on parallel random number generators, that if you need few generators, then parameterization is fine. If you need a large number of generators, then you have to use splitting, and depending, and if you really want to use a Merson Twister, then you need to carry a huge library with you. There are alternatives I present here. So the first one is called SPRNG library. This library is a C++ library dedicated to parallel random number generator. which is somehow a mixture between parameterization and splitting. It depends on the generator used, and you have many different generators inside, and and another solution is the RNG stream library developed by Pierre Lécuyer. Some of you may know him. This is also a C++ library dedicated to parallel random number generator, and it only implements splitting. Okay, this is based on what's called a multiplicative recursive generator, a combination of all this actually, of such generators actually. And once again, each stream of the generator is uniquely identified by an index, so it's very easy to map a processing unit with the generator. Well, this was all I wanted to say about random number generators, and so although there are still many slides left, I won't go through all of them, so don't panic. We've put all these slides in so that you can have a look at them on your own, and we can answer questions tomorrow or even later in the evenings. I just want to give you the basics of OpenMP, just to explain the methodology and how it works, and then we'll use it in the training session tomorrow. OpenMP actually provides high-level thread programming. This is let's call it library, even though it's not entirely true, because most of it is made of pragma. There are actually very few functions. So this is something implemented in the compiler actually. Okay, but OpenMP targets shared memory architectures. Okay. And this is based on a fork join pattern. Basically, the execution of an OpenMP program looks like this. You start here, and you have one process, one thread. And then you come across the first parallel instruction, and at this, when crossing this instruction, then a pool of threads is created. So you have somehow the main frame, which is split like this, and then all the threads are executed in parallel till the end of the parallel region, and then the main frame execution goes on, and then you come across a new parallel instruction. You have new threads created. They just all join together, and this goes on like this several times. Of course, creating threads, so this is the fork part, and then collapsing all of them, so joining them. These two mechanisms take time. So, when you create threads, you definitely want to keep them alive as long as possible. It's a very good idea to spend all your time creating and destroying threads, because it's just a waste of computational time. Okay. So from a practical point of view, to start writing an OpenMP code, you just have to include this file with everything defined inside. And OpenMP instructions are actually defined as pragmas. So you just add such instructions in your code, all starting with sharp pragma OpenMP, well, OMP, which stands for OpenMP. And then this start will be completed with several instructions, and I will detail a few of them afterwards. And then to compile, you have to, you need this flag either for compiling and linking, and this is valid for the GNU compiler and also the Clang compiler. Okay. Well, you see here, so your main thread divides in 4 threads here, but here in only 3. So you can actually monitor the number of threads you want to create each time you encounter a parallel instruction. And this can be modified by this variable. If you don't set this variable before running an OpenMP code, it will just use as many threads as well as the number of cores on the machine. And even sometimes it also takes into account the number of virtual cores. Okay, so this is usually a bad idea to take all the resources available on the computer. We'll talk about this tomorrow at the beginning of the training session, because this is very much related to to how efficiently you can access memory. So here is a typical example of an OpenMP program. So you have your include, you have some serial stuff, and then you say, well, from now on I would like to create a parallel region, and in this parallel region these variables will be private, so it means that each thread will use its own copy of the variable, whereas this one is shared between all the threads. So this means that if var3 is modified by one of the threads, it will be immediately visible for all the others. So you have your parallel region, which ends here. Then you may have sequential code and a parallel region again, and so on.
Can I ask you?
Yes.
How do you access variable 1 and 2 in the serial region after the parallel one? Because you must have then a number of variable 1 and 2 for each thread, and so you may want to access them separately.
Well, okay, so your question is actually, what's the value of, let's say, var1 when you're at this level and you're back in the main thread? This is not clear. Well, there's a way to tell that you would like to keep in the main thread the value that was in this variable in the thread that finished last. But obviously you don't know which one finished last, so I think that it is mostly useless. If you say that your variable is private, then well, I'll come back to this later on, because well, there are several situations in which you would like to do this. Because what you have to keep in mind is that if instead of doing this, you could have decided not to declare the variables there, but directly inside here, and they would have been private just by definition. So if you do it this way, it means that when entering here, these two variables are actually copied for in all the threads. And only native types can be copied. Yes, yes, at different places in memory. This is what I mean by copied. So just to go on this point, to continue on this, for instance, if this variable had been a pointer, then you would not have been able to declare it private. This is something very important. A pointer can never be declared private. Simply because there's no way for the operating system to know how much memory should be copied to have another valid pointer of the same type.
But then, yes. If you copied all this variable in the different threads, then you will have the address of each of them, and then later you can access each copy separately.
Can access each copy separately. Well, of course, the variables are copied at different places in memory. Okay, I agree with you on this. But then I'm not sure that there's any mechanism ensuring that these addresses are still valid once the parallel region ends. Something may have been written there. There's no reason why it should be valid. I don't know if you have something better to... What happens when you're there? So the parallel region is over. On what happens on the copy of these?
What you do is the address of the first declaration.
Yes, that's the only thing you can do. So I don't think you can have access to the private variables once the region is over. Okay. Okay, well, and shared is simple. It just means that it's this.
We need to private this variable.
Well, and shared just means that it's the same address that's used for all the threads. Okay. So to create a parallel region, you just use this instruction, and everything inside the braces here is executed by all the threads. Okay. Well, of course, you can modify by adding some stuff in between here, and I'll just give a few examples after. And so the default for all variables is that they are shared. This is the default. You can say, I don't want any default policy on this. I want to specify for every variable what I want to do. This is just to be sure that you haven't missed some important points. So you can just say, no default policy for me. I want to make everything explicit. And then you have to, this is a typo, you have your shared variables and your private variables. I don't think public exists. Don't think so. So here is an example. Yeah, so in this example, everyone prints its thread number, and then the one with thread number 0, which is usually considered as the ancestor or the main thread, although it's just a convention, also prints the number of threads. So this variable, which is the index of the current thread, is declared private. this declaration could have been moved inside here. Okay. So here you have a new instruction, which is this instruction, OMP barrier. And so this instruction tells every thread to stop at this point in the execution until all the threads reaches it. Okay, so it means that this cannot be, this line cannot be printed before all of them have already printed this. Okay. So I said at the beginning that OpenMP was not really a library because it was mostly made of pragmas. So these are the few functions available in OpenMP, plus one for measuring wall time. So you can get the number of threads in a parallel region, the thread number in the parallel region. You can fix the number of threads to be used, and you can turn on or off nested parallelism. Of course, in principle, nothing prevents you from having a parallel instruction, so a pragma OMP parallel inside another one. So you may want to create a second pool of threads inside an already parallel region. Well, it can be done, but then you have to make sure that you have enough resources on your computer. And I wouldn't really encourage this. So there's a way to tell within a parallel region that the next instruction, the next few lines should just be executed by a single thread. This is the purpose of single. Master does the same thing, except that it ensures that this is the thread 0 which will execute it. Okay. And then you have a few things. So barrier I already said. Well, ordered is something quite strange because it just tells you, okay, execute this in parallel, but don't change the order of execution. So imagine you have a loop. It tells the iterations should be run in order. So there's no much parallelism left. Most important instructions are these two. It's quite common that within a parallel region you have what I call a critical instruction, an instruction that should be executed by all the threads, but one at a time. And there are two ways to achieve this, either to use critical, and this is to be used when you have several instructions that are actually that should be executing just one at a time. If it's just a single assignment statement, then you should use atomic. And okay, this is the country that you should read here. Atomic is much more efficient. Okay. But what you can write here is something this is an assignment with basic elementary operations, plus, minus, multiply, divide, and that's all. And this is, this is something related to, I will talk in a few slides, called reduction. Sometimes you have variables that you would like to be shared and private at both times. This is obviously not possible, and usually it's because you want to do what we call a reduction, and I'll come back to this in a few slides. Okay, just skip this. I already mentioned shared and private. This one just forget. And reduction is important. Where's the example on reduction? I'll come back to reduction afterwards. I thought I had an example there. Okay. So I've mostly already talked about this. An important, a common instruction when you're using OpenMP is to parallelize loops. And to do so, you use OMP4. So this has to be used inside an OMP parallel region. So you have Pragma OMP parallel, and then inside Pragma OMP4. These two can be collapsed in one, and you can actually come through Pragma OMP parallel 4. Okay? And we'll see examples of this tomorrow. You can actually influence the scheduling of the iterations of the for loop. I just skipped this. And then reduction is, I just would like to finish by talking about reductions, but oh yes, this is the example I was looking for. So assume you want to do this in parallel. So you want to, let's say, compute the, the norm of a vector or the dot product, no matter. Okay, A is only accessed for reading, so no problem. But then the variable sum will cause you a bit of troubles because as each thread will write in it, you would like it to be private. But then at the end, you would like the overall result. So you would also like it to be shared. And it's not possible. It's just, so this is a typical example of what we call a reduction. So here is the answer. So you say that sum is actually neither shared nor private, but a reduction for this operation. And what happens transparently for you is that inside each thread, a local copy of sum is created and is used as a local accumulator. So you have in each thread a local sum, actually. And just before quitting the parallel region, there are some atomic operations just to sum up all the local sums. And instead of doing this, you can just use reduction. Okay. This is the same. This is the same example. This I skip, and I think that nested loops we'll see later. Okay. So just one or two things before stopping. One very, very common mistake when using OpenMP is what we call race condition. It typically arises when you have a shared variable accessed for writing by two different threads at the same time. And this is something obviously impossible. It may be very difficult to notice it. But very often, actually at least under Linux operating systems, when you write an OpenMP code and you have the feeling that it takes ages to run, whereas the sequential version was much faster, it's probably that you have a race condition. Because the operating system takes care of it for you and knows that there's a race condition, and so everything is done so that the execution can go on. So This is one way of, well, this should ring you a bell and say, oh, there's probably a race condition. Okay, I think I run over my time, so I'll stop here. Do you have any questions on this? Yes. Well.
Okay. Anyway, before you showed us an example of like OMP4. Okay. And in that example, you had a 4 inside a parallel section. So let's say stop into one of them.
Where was?
Let's say this one. Okay. In this case now, how does in reality the number of threads influence this 4? Because let's say here I have n operation to perform, and let's say that I have a number of threads that is not n. What is happening in reality?
So what happens in practice is that the n iterations here are split among the number of threads you have decided to allocate to your, okay.
And
so let's say you have 2 threads, and your question is, what about if n is odd?
I don't know, yeah, for example.
Well, this is probably handled by OpenMP. Actually, I never told you that these iterations were split in 2 blocks. I skipped a slide on the scheduling of this instruction, but there are several ways of splitting the iterations here. But no matter the way you choose, all the iterations will be run, even if you cannot properly divide n by the number of, everything is taken care.
By OpenMP.
Sorry?
By OpenMP. OpenMP does everything.
Yes.
You showed the after that the operator atomic reduction. Yes, this one. Is there some kind of guarantee on the order of the reduction? For instance, if I want to be somewhat smart numerically and I sort my array before doing the summation, and then I want to sum it with the OMP parallel, the blocks, are they going to be reduced in some kind of order, or is it completely implementation dependent?
I don't think there's any guarantee on this, and I don't think that you can influence this. So your question, if I understood it well, is what's the order in which the local sum are reduced together?
Yeah.
Yes. I don't think that you can monitor this. No.
Okay, thank you.
So I have just a comment about the option order that you said maybe not very useful, because then it transforms a parallel session into a sequential one. But then I'm wondering whether, since you said that it takes time to create the threads and to destroy the threads, so it might be convenient if you have a sequential bit inside the parallel one to put ordered in order to speed up and avoid the creation and destruction of threads.
Well, not necessary to put order, but sometimes it's more efficient to well, I don't have any. I don't have an example at hand for this, but sometimes when you have, let's say, two parallel regions and well, some sequential operations in between, it's more efficient to actually execute this sequential part on all the threads, even though you would actually only need one to do it, just because by doing so you just keep the threads alive, and well, and that's cool. Or you can use a master instruction, for instance, and so you say, okay, it's just the master thread that will do it. It depends on the example.